All right, great. Hello and welcome to Embedded TV. In this episode, I'm going to be looking through the sigma delta modulation. It's a very simple modulation technique which is used by digital microphones and certain ADCs. And it's actually pretty cool because it means that you can easily connect the digital microphone into an FPGA and demodulate the analog signal because it's just a single stream of ones and zeros. Without going into too much theory about PDM, you can always look it up on Wikipedia or elsewhere on the internet. I'll just dive directly into the C code that modulates and demodulates the signal. So let's do exactly that. First of all, I'm going to show you what it looks like. So this is a graph in GTK wave that shows the PDM signal and the corresponding analog signal. So the PDM signal is basically a stream of ones and zeros, and if the signal is in the middle, it becomes just an alternating stream of ones and zeros. So when you have a microphone that is outputting PDM, you actually sample it at a very high rate. So the rate would be somewhere around 4.8 megahertz for a sound at 20 kilohertz. So you have to have a much higher sampling rate, and that is one of the drawbacks of PDM. But it's still not as high as it's still not higher than what is reasonable with consumer electronics like microprocessors and lower end FPGAs. So it's still like for lower frequency signals it's perfectly fine. For high frequency signals it would be hard to reach the kind of sampling rate that you would need in order to sample the signal. But for microphones and for audio, it's pretty much the perfect modulation. So how do we actually generate this stream of ones and zeros? If we go to the C code that I have written here, this is actually where I generate this GTK wave file. So we start off with a signal, and for the signal I've chosen just a sinusoidal signal with 4 periods and a frequency of so basically just a signal of 4 periods, and we have 512 samples. We start with a signal, and then we just we keep the value of the PDM value. It's going to be either 1 or -1, and we just keep it in a variable on the side. And we have an integrator where we just take the signal and we just subtract the PDM value. And if the integration, the sum of this integration is above 0, we set PDM to 1. If it's below 0 or 0, then we set it to -1. And this is it. Like this is all you have to do. And the resulting average value of ones and zeros in this stream becomes the analog signal. So if you want to decode the signal, all you have to do is just sample the stream of ones and zeros, and count the number of ones in that sample. And there is a very fast way of doing it on the processors that support it. And on the processors that don't support it, you can still use the same method, except that it's going to be compiled into much slower code. And for that, I use the GCC function called pop count, which counts the number of, it basically stands for population count. It counts the number of ones in a number. So I use a buffer of 32 bits to keep the incoming samples. And I basically just take into this. I basically just push the samples into this buffer. If the sample is 1, I just set the bit. If a sample is, ideally I don't even have to do this reset of a bit, but I just do it just to be consistent. So I just push the bits into this 32-bit integer. And to convert that into a sample back into the analog signal, I just use a built-in pop count, and this will, on the processors that support it, will actually compile into very efficient code. And then, because I have 32 bits, I subtract 32 bits or 16 bits just to get it into the range of -16 to 16. And then I scale it up so that it becomes a value of 0 to 255. And I can then filter the signal to get the original analog signal. So it's extremely simple. If we look at what it looks like, if we go back to the VCD file, VCD stands for value change dump. It's also a nice, very simple format to inspect waveforms, and it's also simple to output out of microprocessors at a high pace, because you're just basically outputting deltas of the variables. So I can just add all of these variables, and I can have a look at what this looks like. So we have our original signal, which is the analog. I'll convert this to analog. Let's see, let's do that, and let's convert this one to analog as well. And we have the PDM signal. And the reason that, the reconstructed signal is always going to be slightly behind the original signal, and that's because of this buffer that you have to push bits into. So it's always going to be behind by the number of bits that you have to sample in order to reconstruct the analog value. But since you're sampling at such a high rate, it doesn't really matter in the end, because you will basically be just a little bit behind, and you always have this delay when you have any kind of low-pass filtering, and the sampling and counting of ones in this running buffer is kind of like a low-pass filter. It basically takes the average of its average number of ones in the signal over time, and you can of course filter it with. There are other filters to filter. There's a Sync3 filter that's popular to filter the PDM signal, but it's a little bit more complex. Like, this is the simplest way of just converting it into a value, and that's it. So you get your analog signal back here from this stream of ones and zeros, and that's how you can read a microphone that outputs a PDM. So I hope you learned something, and I'll see you later. Subscribe to my channel.